We live in such an uncertain world, but we have to make decisions and move through that world, and Bayes helps us do that.
When you think of the subject of history, the first things that come to mind often include war, tragedy, and political turmoil. But believe it or not, seemingly unrelated subjects, such as math, have more of an impact on society than we know. Through this documentary, we hope to make you recognize the mathematical and technological revolutions and reforms that have occurred thanks to a much-forgotten man named Thomas Bayes. Thomas Bayes was born in 1702 in London, England. Young Thomas was privately educated and was raised by his father, a nonconformist minister. He continued on to the University of Edinburgh and then went back home to assist his father at his church. After he became the minister at a church in Kent, he moved to Tunbridge Wells. During his time there, he wrote just 2 published documents. One of those regarded religion, while the other involved mathematics. The theory Bayes is known for, however, was not published until after his death. This amateur mathematician is responsible for one of the most influential ideas in history.
Bayes' theorem is a way of combining evidence in such a way that, given evidence for one hypothesis and some expectations of other hypotheses, you can combine the types of evidence in such a way that the 2 pieces of evidence taken together strengthen the conclusion.
After Thomas Bayes' death, his friend Richard Price published his theory posthumously. During the same time that Bayes was working on his theory, the scientific revolution was in full swing.
There was a big religious issue at the time about cause and effect. And God was called the primary cause. He was the cause of creating the world. A lot of scientists justified their science by this reasoning that if we can understand the world enough, we can figure out God. And Bayes flipped it around.
At this time, probability was based upon the number of times an event had actually happened. The people who believed this were called frequentists. These so-called frequentists proved to be a tremendous roadblock to the theory later on. The frequentist definition of probability is the long-run expected frequency of occurrence, while the Bayesian view of probability is related to degree of belief. It is a measure of the plausibility of an event given incomplete knowledge. The frequentists were in power for decades until several different mathematicians revamped Bayes' initial theorem. "20 years later, the scientific community faced difficulty in utilizing data. Scientists had observations from the Greeks, Romans, and the Arabs, but each was different. In order to use the most accurate observations, scientists chose to average the data. Of course, this process was still not accurate enough. Thus, the world needed a better way to handle the data. A young mathematician named Pierre-Simon Laplace believed that probability could be used to find the answer. He rediscovered Bayes' mechanism independently and published it more than 20 years after its inception in 1774. Laplace explained the principle in new terms. The probability of a given cause, given an event, is proportional to the probability of the event, given its cause. Laplace felt confident that his theory was applicable to many facets of science. A friend of Laplace used the theorem to calculate the masses of Jupiter and Saturn. Today, our advanced technology has proven that he was up to 99% accurate. Laplace used his mechanism with testimonies in court, made advances in astrology, and determined that there was a natural law in place. From this point, scientists began to find natural laws to explain phenomena without relying on a divine presence for answers. After 40 years of work, Laplace improved Bayes' original theorem and became the world's first Bayesian. With the improved theorem, the government began to collect data on a number of things, including cholera victims and the chest sizes of soldiers. But a drastic change had occurred in the scientific community, which decided that no one could longer rely on probability to prove anything. John Stuart Mill denounced probability as ignorance, coined into science. Thus, once again, Bayes' theory fell into decline, at least with theoreticians. Various uses were found for the theorem throughout the duration of World War II.
It was used by the artillery in France and the United States and in Russia to test ammunition and to guide the artillery fire. It was used in a lot of places during the war for the reason that you couldn't sit around waiting until the war was over.
During World War II, German U-boats were posing a serious threat to Allied forces. Naval supply lines were cut off. and without them, countries could not support their citizens. Allied forces had difficulty finding the U-boats to attack, and all messages they intercepted were encrypted and unusable. Alan Turing was employed to crack the Enigma code, so he built a machine that could test each code separately. This process was still extremely slow, so Turing used a Bayesian system to guess letters. With each letter the Bayesian system produced, more information was added to the machine, speeding up the process. Turing was able to crack the Enigma code, but the information was still not enough. Messages could be decoded, but the information gain only narrowed the search for German U-boats to a 236-mile diameter. Mathematician Bernard Koopman was hired to assist in finding a solution to crack the code, and blatantly used Bayesian principles to find the answer. He began by assigning a 50% probability that the U-boat was in the 236-mile diameter. As more information came in, the probability was increased until Allied forces could easily attack the U-boats. It is believed that the use of Bayesian principles helped end the war 2 years earlier. A few days after the German surrender, Churchill ordered the destruction of all evidence of decoding to prevent the Soviets from learning of their progress with decryption. Once again, Bayes' success went unrecognized. The late 1970s and early 1980s sparked a new phase of research into a variety of mathematical ideas. The most common theories concerning probability being investigated included Markov chain, Monte Carlo, and Gibbs sampling. However, they all failed when it came to consistent reliability. Bayesians Alan Gelfand and Adrian Smith began researching independently. After scrutinizing over these theorems for months, everything suddenly clicked, but they predicted other researchers would soon follow in their discovery. They worked briskly yet cautiously to write a paper summarizing their findings, which they hoped would bring new light to Bayesian probability. They used the word Bayes only 5 times in the 12-page paper, which was considered an amazing feat in an age where any author suggesting the use of Bayesian analysis was criticized for being ludicrous. Gelfand and Smith found the outcome of the publishing to be quite displeasing. While Bayesians worldwide thought of their connections between various theories of revelation, the paper had very little to no outreach in the statistical and scientific communities. Nonetheless, Bayesians used this paper, entitled The Watershed Synthesis or Markov Chain Monte Carlo, to solve problems that for 2.5 centuries had only been dreams, in the words of expert Sharon McGrain. But the revelations sparked by Bayesian probability were not through. In 1991, Adrian Smith's student, David Spiegelhalter, developed and produced bug software, standing for Bayesian inference using Gibbs sampling. Finally, the world had realized how important Bayes' theorem was. By means of the bug software, people from every realm of the scientific and technological world could use Bayesian probability. Because there were so many methods of Bayesian probability problem solving in the software, each researcher could choose which one he best saw fit. Bayesian probability had been perfected, made impressively reliable, and incredibly versatile in terms of where it could be applied. Almost overnight, Bayes, Laplace, Koopman, Gelfand, Smith, Spiegelhalter, and the rest of the world's Bayesians became respected mathematicians after centuries of having their work being referred to as illegitimate and preposterous. As the saying goes, the only constant thing in today's society is change. Something virtually non-existent has evolved into one of the most life-changing ideas. Before Bayes, it was impossible to predict the likelihood of a certain event that had never occurred before. But today, with the help of Bayesian probability, we have been able to make astounding advances in many fields, including genetics, genomics, and neuroimaging. This theorem spans much wider than the scientific community. Everyday people can potentially apply this theory to simple matters, such as where the 8-ball will land in a game of billiards, or how likely it is to run into someone you know at the grocery store. We use some form of Bayesian probability every day. Think about it.